Okay, so before we begin today, I just want to give you a preview of what the next 5 weeks are going to look like and what the story is really going to be. So the story for the next 5 weeks is we're going to answer some important questions. But before I tell you what those questions are, let's go ahead and kind of set a story. Let's recap what we've done so far. So previously, we've done the geometric vector form for lines. So for example, you might have a line that looks like that. And this line is simply a line that takes the vector 1, 2. It'll take this vector, and it traces out that vector and creates a line. So it's going to create this line right here. But I can also express the same line using a different vector. I can do -2, -4 times another scalar s. And this is now just going to be a different vector, in this case, -2, -4. And it's now going to trace out the same line. It's the same line that gets traced out. So there's two different ways to express the same line. In this case, they're just simply multiples of each other, and it's very clear that they're in the same direction. But when we go up to the next dimension, say we go to planes, and let's take a plane in 2 dimensions, so it's just going to be the entire R2. Well, one way we can do that is we can express it as a combination of these 2 base vectors, these standard basis vectors. And so what this means is we can take any number of steps in one direction, in the x direction, and we can just do this any number of times. So what's going to end up happening is we can move like this, and we can also move up and down in the second direction. And we can get to any point in R2 using these 2 vectors. Using these 2 vectors as our steps, we can get to any point we want to in the plane. But one thing to consider is it's not actually necessary to use these 2 vectors. So for example, we could, if we wanted to, use different vectors. We could use 2 different vectors here. And these are just going to change the steps that we're allowed to take. So now instead of using 1, 0, and 0, 1, we're going to go ahead and use 1, 1, which is just a vector that goes up 45 degrees. And we can use this other vector, 1, -1, which looks like this. And you can see that these 2 vectors span the entire plane. They're going to span the entire plane. In both cases, you can get to any point in R2 by using either of these steps. We have 2 different ways of representing the same thing. And so one of the conundrums that we want to be able to resolve is, how do we know if we have enough vectors? How do we know if we have too many vectors? And more specifically, which set of vectors is best? Is it better to use the one that I have on top? Arguably, this is the first one that would come to mind. Or maybe under some circumstances, we'd want to use this different representation of R2, taking these abnormal steps. So a couple of the questions that we want to answer concretely are goals in this vein. Is you want to answer the questions, which vectors should we use? How do we know we have enough? Or too many? And specifically, are any vectors redundant? Okay. There are a couple other things. We want to be able to choose a very nice set of vectors to express our lines, planes, and hyperplanes. So one key property that we might be concerned about is, do they maintain distance? Is the distance of the vector that you express using those combinations easy to calculate? right? And lastly, what are the algebraic and geometric properties of these different choices? So maybe a quick summary of all of these questions is simply we want to be able to change these different choices of vectors. We want to change these vectors that we choose. They're used to span these different lines, planes, and hyperplanes. And we want to choose them in a meaningful way. And arguably, there's no best way to do it. These are the two equally good ways of doing it. But depending upon the exact context, you may want to prefer one way over another. And we want to be able to resolve for which instances is it better to choose one choice over another, and vice versa. Before we get started today, we're going to need a few definitions. And so one is the span. So I've already alluded and used the word span, but a span of vectors is simply the plane or hyperplane or line that contains all of those vectors. Right? So for example, we might take something like this. We might ask, okay, what does the span of this look like? Well, we already drew the picture of this before. The span of this would be the line, plane, or hyperplane that contains both of those vectors, and hence all combinations, all possible linear combinations of them. So geometrically, what is this going to look like? This is going to look like the picture we got before. You have all the possible, it has to be a plane. You have to be able to move in the 1, 1 direction and also in the 1, -1 direction. So geometrically, this is going to form a plane. It's going to form all possible combinations of these. And algebraically, this is going to look like all possible points all possible vectors of the form 1, 1 plus 1 minus 1. And you can scale each of those vectors by that amount. So these are the same idea. This is what a span is. And in reverse, we have something called a basis. We're going to get in detail later what a basis is and what the requirements for really specifying the basis of a line, plane, or hyperplane. But a basis of a line, plane, or hyperplane is a minimal set of vectors needed to span it. So for example, this plane has a basis that's exactly the vectors that I indicated. But on the other hand, it could be the case, if we go back before, let's finish this definition first. Minimum. So it's a minimum set of vectors that span it. So to go back up before, if we go up to our example we had with the plane with R2, you might say, okay, I also want to allow steps in the direction 1, 1. So this is, you have 3 directions you're allowed to move, but you'll notice that adding this new direction is now redundant. It doesn't get us anywhere new we couldn't get before. So this extra direction is redundant. So we don't actually need it in our basis. It's not going to be included in it. And this is one of the questions we want to be thinking about. If I have a line, plane, or hyperplane, how many vectors do I really need? And how do I know if any of them are redundant? And the minimum such vectors is a basis. So much like the cardinal directions, east, west, north, and south, the reason we only really have 2 directions, east, west, and north and south, is because the surface of the Earth is a 2-dimensional surface. We only need 2 directions to do it. We don't need a 3rd direction. Every third direction is a combination of the previous two. And so this is the kind of thing we want to be thinking about. Okay. Just for emphasis, we're going to talk a lot more about a basis and what a basis is later, but just understand going forward that this is kind of the answer to our conundrum. How many vectors do you need, and how do you know if you have the right number and you have none that are redundant? That's what a basis is going to be. Okay, today's focus is going to be on two special lines in hyperplanes. The first one is going to be called the kernel. The kernel is a very special line plane or hyperplane, which is simply the solution set to ax equals b. So sorry, ax equals 0. So this is something you already know how to solve. So you actually already know how to find a kernel. When you solve this equation and you put it in geometric vector form, you're finding the kernel of that matrix, of that linear transformation. So to put this in perspective, let's just do a very quick example. We'll do a more detailed example later. You might have a matrix that looks like this. You have A equals this. So keep in mind, the matrix is actually a function. It's a function. This function goes from R2 to R2, right? Because if you multiply it by a vector, you get another vector. And so we can think about what this actually does. So let's do a quick before and after graph of this guy. What's going to happen is we're going to take a couple vectors. So here we have 1, 0. That's going to transfer over to 1, 1. You have, this is 0, 1, which is also going to go to 1, 1. And then you might have minus 0.7, minus 0.7, which is going to go to minus 1.4, minus 1.4. And so you'll see that no matter what vector you pick, right, you're going to get something on this line. So no matter what you pick on this entire circle right here, you're going to get something that this circle is going to get squashed onto this line. But some of those vectors, some of those points are going to get squashed onto the origin. And so the set of points that get squashed onto this origin, in this case, all those orange points, no matter where you go, get squashed this origin. This is the kernel. So this is the kernel of A. It's the solution set to AX equals 0. So the kernel of A is going to live in the before area, the before set, or the domain. And it's just the set of points that all get squashed to it. All right, so that's what the kernel is. Let's have a meaningful application example. So we're going to run a little toy example. So in this toy example, we're going to buy some toys. So you can buy $5 for a boat, $1 for a plane, and $2 for a sub. Right? But we're going to have an additional requirement that maybe seem unusual. When you buy the toy, when you buy the toy boat or the toy plane or the toy sub, you also want to give away with it 5 toy soldiers. Okay, so this is kind of artificial. It's a kind of a fun example. You can imagine that maybe instead of toy soldiers, they require ammunition, or they require fuel, or they require labor. They require something that's independent of money, something that's not the same thing as money, that you can't just purchase outright. But in this case, your niece or nephew is going to demand that every toy they get come with 5 toy soldiers. So what this means is that the cost of each thing is actually a combination of both dollars and toy soldiers. So we have a boat costs $5 plus 5 soldiers. All right. And a plane costs $1 and 5 soldiers. And a sub costs $2 and 5 toy soldiers. And so what we can do is we can model this with a linear transformation. So this linear transformation, we can take the number of boats, the number of planes, and the number of subs, and we can output this as the total cost. This is going to be dollars and soldiers. So if you tell me how many boats, planes, and subs you want to buy for your little niece or nephew, this transformation is going to answer the question, what does that cost in both dollars and soldiers? So in this particular case, we're going to have how many dollars? Well, the total cost is 5 boats. We'll make that X plus 1 Y. Just for emphasis, we're going to make this equal to X, planes equal to Y, and subs equal to Z. So in dollars, it's 5 times the number of boats plus 1 times the number of planes plus 2 times the number of subs. And the number of toy soldiers that are required is 5 times the number of boats plus 5 times the number of planes plus 5 times the number of subs. So we have this nice little transformation, and you can write this as a matrix. So there's a matrix that categorizes what the total cost is in both dollars and soldiers. And we're going to be interested in the kernel of this matrix, the kernel of this transformation. So maybe one thing is we want to emphasize is what is this really doing? So the key point is the kernel of A details what trades are allowed. Without changing any cost. So if you don't want to change the cost at all in either dollars or toy soldiers, that's going to be encoded by the kernel of A. By the kernel of your transformation, it tells you what are all the different possible exchanges you can make. And so if we go back up to the cost, we can observe, let's just make a quick observation. I could trade 4 boats for 1 boat, sorry, not 4 boats, 4 subs for 1 boat and 3 planes. So this trade right here is allowed because the total cost here costs $20, sorry, not $20, $8 and 20 soldiers. And likewise, 1 boat and 3 planes also cost $8 and 20 soldiers. So if your little niece or nephew doesn't like their gift, you can say, okay, I can trade 4 boats for 4 subs for 1 boat and 3 planes. This trade is allowed. And this is going to be encoded into the kernel, but maybe there's some other trade we can do, like just eyeballing the different prices and the costs for all these different toys and combinations. It may not be clear exactly what all the possible trades are. The kernel is going to detail what those trades are. But keep in mind, those trades have to be exact in both exactly the dollars and soldiers. It has to be the same in all the possible costs. All right, so how do we do that? Well, keep in mind, the kernel of A is simply the solution set to AX equals 0. So what we're going to do is we're going to take this guy right here, and we're going to set this equal to 0. We're going to just augment this with the 0 matrix, with the 0 vector. Right? We're solving here. We're solving, right? This is x equals. So we're solving AX equals to 0. And now it's just a matter of row reducing it and expressing our answer into vector geometric form. The answer we get should include, at least in part, that we're able to trade 4 subs for 1 boat and 3 planes. But the question we want to keep in mind is what other trades are allowed? All right, so let's go ahead and do this. All right, so we're just going to row reduce. We need to reduce the first row by 1/5 to make that a 1. Right, the goal is to turn this into the identity matrix as much as possible. Right, and then once we have that 1, we want to change everything above and below it into a 1. So we're going to take row 2 and subtract 5 times row 1. Oh, this should be a 1/5 up here. That's a mistake. Right, so far we're good. We have, that's a 1, that's a 0. We now want to make that 4. We want to turn that into a 1. So we're going to scale it by 1/4. Again, we want to turn it into the identity matrix as much as possible. All right, so now we're almost as far as we can get. We now need this 1/5. We have all those 1s, and we have this 0. But now we have that 1/5. So we're going to take row 1 and subtract 1/5 of row 2. Let's do this a little more delicately. So we have 1, 0, 0, 1, and this is 2/5 minus 3/4 times 1/5. And we chose, and this is 3/4. So what do we end up getting? If we simplify this, this is 0.4 minus 0.15. And sure enough, we get 1/4 on top and 3/4 on the bottom. All right, so this is our final form. This is in reduced echelon form because all of the 1s here are in a staircase manner, and everything above and below those 1s are 0s. What's here on the right is going to encode our vector in just a second. So let's go ahead and translate this into what this actually means. What does this mean? This means this top row here means x plus 1/4 z is equal to 0. And the second row translates as y plus 3/4 z equals 0. And if we solve for x and y, we get x is equal to minus 1/4 z, y is equal to minus 3/4 z, and z is equal to z. And we can put this into a vector, and this is the same thing as minus 1/4 minus 3/4 1 times z. So what does this really mean? This means that the kernel, if we look at the before and after graph, the before is in 3-dimensional space, right? So you might have x, y, and z. This particular line right here is a vector that kind of goes minus 1/4 in the x direction, minus 1/4 in the z direction. So it's a vector that looks like this, and it's a line that you can trace. And this line traces all the possible configurations of boats, planes, and subs that all have a net cost of 0. So one objection you might have is, well, this includes negative subs. Well, this just means you're owed a sub. You can sell a sub. You can sell one of these toys and get back the money and the soldiers that you want. And in the after graph, right, you're going to have dollars and soldiers. Everything on this green line is going to be a net cost of 0. So everything is a net cost of 0. And we're going to ask later, how full is this after graph? We're going to ask that later. But I want to point out that this line right here corresponds to all the trades. And so what does this really mean? This says that one sub is the same thing as augmenting out one boat, one 1/4 boat and 3/4 of a plane. And if you scale that up, that's the same thing as 4 subs is 3 planes and 1 boat, which is exactly what we said earlier, except it's the only trade that's available. You're not allowed any other trades. The only other trades you could do are some doing this multiple times or doing it in reverse. You could trade planes and boats for subs if you wanted. Just do the trade in reverse. But this is what the kernel looks like. The kernel lives in the domain. So it lives in the domain in the before graph, and it's all the points that get squashed exactly to the origin in the after graph. And what it does is it encodes all the possible trades that you can make. So that's the kernel of A. All right, the second special planar hypergraph we want to talk about today is called the image. And this asks the next question, the question we alluded to earlier. It asked, how full is the after graph? So it could be the case that when we spend our money in soldiers, we may not be able to spend them all. So in this particular application, we want to ask, is it possible to spend any amount? Or if not, what possible combinations of dollars and soldiers could you possibly spend? So in this particular case, we're going to ask what combinations exactly could you spend? So to get an idea what's going on, let's just look at what matrix multiplication is from perhaps a slightly different perspective than what you're used to. So in our case, we had a matrix that looked like this. And the image of A is just asking, well, what are the different possible outputs? Right. So in this case, the image of A is equal to the set of all possible outputs. Right. In previous language, you might have called this the range. So you can think of it as the range. But it's not necessarily, in this case, it's not necessarily all of R2. There might be combinations of dollars and toy soldiers that you can't spend exactly. We don't know. Now, this matrix multiplication right here is in fact a combination of the columns. You can write this like this. So another way of looking at what the image of A really represents, the image is also equal to all possible combinations of the columns. So that's another way of looking at what the image of A really is. And so to do this, what we want to do is we're going to go back to the very first example I did earlier, now augmented with our extra graph. So we're going to look at this example right here. And in much the same way, you can go down and you can say, okay, this first red direction that we had, the 1, 0 direction, that was new. When we did it, you couldn't get any of the previous vectors. It's the first one. It's new. The second one was also new, right? You can't go left and right by going up or down. Right? That's what the blue vector is doing, the second vector. And when we added this extra vector as an example, it was redundant because it's in the same plane as both the red and the blue vectors. It's already a direction you can achieve. It's redundant. We don't need it. And in much the same way, what we're going to do to figure out what the image is, we're going to go down the line of each individual vector and ask, is this redundant? So we're going to take these vectors right here. We're going to take these vectors and we're going to go down the line and we're just going to ask, is this redundant or not? So this very first vector, this one's always good. This is always a new direction. So this is the first one. This is good. So we're going to keep this one. So this one means that we're going to keep that one. It's always good. It's one we can use in our basis to describe the image of A. And then we're going to go to the next one and say, is this new? And so to do this for now, we can just do this intuitively or geometrically. As a warning, we're going to do this in a more robust way later, that you'll be able to find a basis for the image of any matrix, however big, later. But right now, let's just focus on using our geometric intuition. So the first vector was 5, 5. So you can always move in this direction. 5, 5. It's a big vector. And 1, 5 is not in the same direction. So 1, 5 is very sharp and up. So it might look something like this. And you can see it's kind of hard, but there is kind of a grid forming here. It's not a square grid like you're used to, but it is a grid, right? And we can concatenate these with more of the same vector if you would like. But now what's going to happen when we go to this last vector, that's 2, 5. If we try to go 2, 5 here, 2, 5 is already a place that we can achieve using some combination of both the blue and the orange vectors. This one isn't new. In fact, if you want, you can actually write 2, 5 as a combination of the other two. It is, in fact, as we discovered earlier, it is a combination of 1/4 times 5, 5 plus 3/4 times 1, 5. So this is not a coincidence that the numbers match up, right? This was the trade-off we found earlier. And this trade-off is going to indicate that this is not new. We don't need this vector to describe the plane that is the image or the set of all possible combinations of the columns. You can achieve every possible cost without ever buying or selling a submarine. That's what this says. I don't need submarines to spend all my money, to spend all my toy soldiers. I do need boats and planes, or at least I need 2 of them, right? We started from left to right. So if you rearrange them, you might get a different conclusion. But if I already have boats and planes, if I'm already allowed to sell and buy boats and planes, I don't need to buy and sell subs. The 2, 5 is a redundant vector to describe this plane. So altogether, we can describe the image of A as equal to the set of all points, that is 5, 5 times some number, right, plus 1, 5 times some other number. You're taking any number of steps in the 5, 5 direction, and you're taking any number of steps in the 1, 5 direction. So just as a quick example to see why this indicates the whole plane, let's kind of redraw the graph we just made at a bigger scale. So you can make as many steps you want in the 5, 5 direction. And you can make any number of steps that you want in the 1, 5 direction. Oops, that's too steep. Right, so you're going to get some grid that looks like this. And now you might ask, okay, how do I get to a certain point? This clearly covers the whole plane. No matter what happens, you can get to a point. So suppose that's the origin, right? And we want to be able to get, let's see, can we get everywhere? How do we get everywhere? Just to see how that happens. Suppose we want to spend $9 and 5 toy soldiers. What do? Well, what we can do is we can buy 2 boats. That's 2 boats. That gives us a total of $10 and 10 toy soldiers. And then we can sell $1. Sorry, we can sell 1 plane. And that gives us back here, which would be 9, 5. Right, so we can get everywhere we want in the plane as long as we're allowed to buy and sell different combinations of boats or planes. And again, this also includes fractional ones, which may seem a little weird, but we can get anywhere we want in the plane. We can spend any amount, any combination to do that. We don't need boats to do that. And that indicates that we don't actually need this vector to describe the image or even to describe this entire plane. A couple words of warning about this particular example is this example seems to indicate that the image of the transformation is in fact everything, but this is not always the case. So to go back up before, we have this example here where we have 1, 1. Right? In this particular case, the image is the aftergraph of the transformation. It's everything you can get out. In this case, you can't get out everything. You can only get out combinations that are multiples of the vector 1, 1. So maybe the final thing to take away from today is that the image is not necessarily everything. So the example we did is it's just an artifact of the fact that we started with a higher dimension than what we ended up with. But even then, it's not guaranteed that you get everything. All right, with that, today's assignment is just to do a couple problems and think about these problems, especially when the image, just think about them geometrically. What does the image really mean? What are the set of all the possible outputs? Don't try to find it using some robust method. We will do that later.